Welcome to Feza Gürsey Center for Physics and Mathematics Higher Structure Seminar Series. Today our speaker is CD from Tsinghua University, and he will tell us about stochastic process and algebraic index, and we thank C for accepting to deliver this talk. So please.
Yeah, yeah. Thanks very much for the invitation. Yeah, this is a really exciting place to talk about the stuff. Yeah, I was looking into the theme of this seminar, so I was explaining something about physics, math, and higher. So, yeah, I want to share with you some of the stuff I'm working on these days recently. So to start with, so let me explain some motivation. I was thinking about some non-productive understanding of this topological quantum mechanics. You can do this categorically, or you can do this in different ways. I'm particularly interested in the probabilistic approach. And so today I will share with you some stuff. I will explain a case study for the simplest example, like topological quantum mechanics. And I'll explain if you explore this and some kind of non-commute geometry and how it's related to algebraic index. And this is this work with my students. And at the end, I'll explain actually a higher dimensional version, a Kyle analog of this algebraic index and these particular things on conformal field theory. So let me start with something very basic. So this kind of usually mechanics is described by an action. So this is an action written on the phase space. So this standard PDX minus like Hamiltonian dt. When the theory actually, for example, when the Hamiltonian vanishes, h equals 0, the theory becomes topological. Let's call this one topological quantum mechanics. It sounds actually quite sounds like trivial, but actually it's not. So I will tell you some story about it. And this is a place you started to see some higher structures arising from these models. But anyway, on this model, like you see, like I'm gonna explain to you the simplest case example first on the circle. And then this topological correlation is gonna be related to, you see, like on the circle, we know it's related to trace and kind of index. And basically the kind of thing I will explain arise from a very simple model, which is called AKZ type sigma model from this mapping space, from this Durham stack to the target symptomatic space. But this is some kind of thing which is the motivation behind. But I will just tell you roughly what's going on. So let me start with explaining some ideas about topological correlation in this approach. So the first main idea I want to explain is the following. Like the way to approach from probability to take the large variance limit is the way to arrive at this kind of topological correlation. So let me explain this in detail. So let's prepare some distribution. So let's prepare a set of like independent, like normal distributions with variance sigma square. That is xnp, ynp, and dqn. I'm gonna put this one, organize this one into two stochastic process. So we're gonna define this Gaussian free fields on the circle by combining these components. Now this is cosine sines, this kind of free modes on the circle. And yeah, let's call this one xt and pt. There are two process, a stochastic process on the circle. And basically, it's about this Brownian motion. But using this Gaussian free field, you can say something good. For example, you can show this infinite sum is L2 converge for every time. And moreover, there exists some kind of continuous modifications, which roughly means like you can treat this process as kind of continuous process in probability. So what can we do with that? like remember, I want to explain this topological action like a PDX. Then I want to define this PDX as a random variable in the following way. So this is my components, X and P. So the direct definition of this one is difficult, but we can use this Fourier modes as a motivation to write down this sums, the infinite sum of these random variables. That's well defined. And you can show like this converge in L2 and converges almost surely. So this is actually a very good action. It's a very good random variable constructed out of this infinite many like Gaussian distributions. Now, this is the stuff I'm gonna do with the topological quantum mechanics, like a PDX, without any Hamiltonian. So now I want to like it sounds trivial, but let me show you something interesting. Now I want to compute some correlation in this model. So take any function on the phase space. Say like take the simplest phase space, like R to n. X is my position, P is the momentum. Now, for any function, I can prepare a random variable like this. So I just replace this x and p by this process at time t. Now, t is a point on the circle. Then you can define the following correlation. So it's defined as follows. Suppose I have some functions on the phase space. Then I define such correlation like this time t0, t1, etc., a point on the circle by the following. So you see, like this is my topological action, and you can think about this one from the path integral point of view. So that's my action, and this is my observable, my quantum observable inserted, the local observable inserted at this point on the circle. Then I compute the expectation value, and now there's the final step, which will play essential role here, is to take the large variance limit. It's like the variance goes to infinity. And for this limit, I will call this one topological correlation. So let's see what kind of properties this topological correlation has. It's actually this limit makes a lot of magic here. So first, let's compute this two-point correlation. This two-point correlation gives the Green's function on the circle, like the inverse of the derivative, time derivative. So if you draw it, is periodic functions like that. So this is XP correlation, and then the XX and PP 2-point functions are zero. So this function G basically is a Green's function on the circle, like the inverse of the time derivative. That's expected actually, because my action functional is PDX, so the propagator should be D inverse. Now we can do a little bit more. So let me show you how to incorporate some algebraic structures, some homological theory out of this data. So first, let me introduce the shifted topological correlation as follows. Like I think about this x and p, my original variable, as like zero modes. So start from a function on the phase space. I look at this kind of a random perturbation, like basically it's a fluctuation by this process at time t. So this kind of like a fluctuation. And this depends on this x and p and also on t as well. Then I can define this topological correlation in the same way. Compute this correlation under this shift by this background x and p in this large variance limit. And this is going to be a function of x and p, that's the background of the shift, and Planck constant h bar, and of course on the depends on the points on the circle. So let me show you some interesting aspect of this topological correlation. First, like you can define this one in a rather general setting. Like for example, you can define this one for Schwarz functions. This correlation turns out to be smooth. And if you calculate this 2-point correlation, like this topological correlation for two functions, And when they're very close to each other, let's say one point approaches the other point, then the limit is basically the Moyle product. So that's a very standard thing you discover in quantum mechanics. This is the Moyle product. So in particular, it has a small h bar asymptotic expansion by the standard formula of this Moyle product on the right hand side. So when h bar is very small, this 2-point correlation is the Moyle product asymptotically by this formula. And many things like that happens. So now let me show you like how to organize this data by introducing the so-called quantum product. I call this one S1 quantum product. It's actually the one-dimensional analog of so-called two-dimensional topological B model. So this is actually one-dimensional B model in the story of mirror symmetry. But let me just show you what this one is. So let's start with something in elementary school. So suppose I have, say, like let's look at polynomial function on the phase space. So A is my polynomial ring. And we all learned from elementary school that we can have a multi-product. Suppose I'm given like a bunch of polynomials like f0, f1, etc. to fm. Then I can simply multiply them together. So yeah, everybody learns this from elementary school. Now next, I want to show you like how to quantize this multi-product. I'm gonna promote this one I'm gonna call this one S1 quantum product. I'm gonna use this notation. So I put a bunch of functions together, and what's up? Like S1 means like S1 quantum product. It's gonna be valued in this polynomial ring with one more variable, like h bar appeared here. That's the quantum parameter. So how this works, and here's the definition. This is my definition for this S1 quantum product. So basically, the idea is the following. I plot this function f0, f1, etc. on the circle at different points in cyclic order. So it means like t0, t1, etc. In this way, it's like a clockwise cyclic order. Then I compute their correlation function. This is a topological correlation I just explained. Then I let them run over all points on the circle, preserving this cyclic symmetry. So basically, you integrate these local correlations over basically this cyclic component of this configuration space of the circle. So basically, you compute local correlation functions and let them run on the circle, preserving this order. Then you see like, because this one depends on x and p and also on the h bar. So the value of this S1 quantum product is going to be a function of x and p and h bar. So that's my definition. So it's a very constant definition, quantum correlation. So let's take a look at this definition. Basically, it can show first the classical limit of this S1 quantum product is precisely the elementary multi-product of these functions. This is just because in the classical limit, there's no correlation. You multiply them together, there's no OPE, and this integration just give you a normalization like 1. So, but at the quantum level, you have this kind of a OPE, and this you can calculate this one, for example, in terms of Feynman diagrams or things like that. You will have this higher h bar order correction. And you can actually compute, for example, if you compute the S1 quantum product for, like, say, 2 functions, and you will get some formula like that, which is very similar to Moyle product, but it's not. It's related to circle S1 geometry. And you can do a couple of calculations to let me just illustrate a bunch of examples to show what they are, like 2 points. You can calculate the 2 quantum product or 3 quantum product and so on. So you can see how these quantum corrections are received along this process. So this is the definition for this S1 quantum product. And you might like wonder like what's the role of this S1 quantum product and what kind of structures it has. It turns out that it has a very remarkable algebraic structure, and this is how it's going to be eventually related to index theorem. So let me try to explain this. So to illustrate the algebraic structure of this quantum product, so I will show you like how this is related to a quantum version of HKR. So let me explain what this one is. So so first let me explain a so-called Hochschild homology. I guess most people know this, but let me still just quickly review what it is. So suppose A is an associative algebra, then we can write down an interesting train complex as follows. So the pth component of this train complex is given by this p plus 1 tensor. And then there's a differential here. This differential is called Hochschild differential. It acts on these tensors as follows. So first you multiply the first two elements, A0 and A1, and minus A1, A2, and etc. is alternating. And finally, you have to add the term like the multiply the last AP to the front A naught, and with the correct sign. It's alternating anyway. And you can check this B squares zero. So it really defines a differential. And the corresponding homology is called Hochschild homology. Okay, so it works for any associative algebra. Now, what's the meaning of this Hochschild homology? So there's a famous theorem by Hochschild, Kosten, and Rosenberg, which says the following. So let's go back to the standard this community word. So let's look at, let's say A is a polynomial ring from our standard flat like a commutative space. Let's let omega A to be like the differential forms on the space. Then this HKR theorem says like if you calculate Hochschild homology of this algebra, this polynomial ring, you find differential forms. And this works for other more general versions. So I only stated the most simplest case. But from here, you can sort of feel that this Hochschild homology plays the role of these like differential forms. And how this is precisely related. And this isomorphism arises from the following map. So let's call this one a HKR map, which sends a Hochschild chain. Let's say here a bunch of tensors to a differential form. This is the most naive way you can cook up a differential form out of functions like this. F0, df1, df2, etc., and some kind of normalization. And you can show this map, sigma, intertwines the Hochschild chain complex with the zero complex on the right-hand side. The the complex, the differential forms with zero differential on the right-hand side, and it's actually a quasi-isomorphism. So if you pass to homology, you get this HKR theorem. So this map is very illustrating, and then this way to connect this non-community world with the community world. Now let's let's look at this one from a different perspective. Again, for this function, we know in quantum mechanics, this is like a phase function, functions on the phase space has a canonical quantization, say into the wire algebra. And this star is the Moyle product. And I just mentioned like for polynomial algebra, this asymptotic formula is exact and is given by the following expression. So this is the Moyle product. Yeah, it's very standard thing for like understanding quantization on the phase space. Then you may ask the question like, well, suppose in the quantum world, I want to understand the Hochschild homology of this Y algebra. And this supposed to be supposed to give a quantization of whatever we just have described. And how this works. So I would describe a quantization of the HKR map from the the quantum correlation function I just described. But how this works, it's actually very simple. You see, like this classical HKR map just maps like this bunch of tensors to F0, DF1, DF2, etc. So when we write down this differential form, you multiply this coefficient. So I simply do a quantum multiplication. So this means like this is differential form. I need to basically put all these dxi's, you take a derivative, and put all these forms outside. And for the coefficient function, I compute the S1 quantum product. So this is a natural thing you can get a differential form and valued also with H bar valued. So let's call this one quantum HKR map. It's a very naive thing you can think about. It turns out to be the correct one. We see like from the description of the quantum product, we see like at the classical limit when H bar goes to 0, and this one is really the classical HKR map. Then, so you see like this is if you use this one as a definition, then let's try to see what kind of structure this map is. It turns out that the following holds. This map actually is a map of chain complexes from the Hausdorff chain complex of the wire algebra. So the left-hand side, you see like the polynomial rings. This top polynomial ring is quantized to this wire algebra. And the right-hand side, originally in the classical case, we have differential forms with zero differential. But now we turned on the differential by this delta. Delta actually in gauge theory is a very famous operator. It's called B-way operator, arise from the general setting to quantize like series with gauge symmetry. But here, this operator delta is just a derivative, lead derivative with respect to the Poisson bivector. So this is also a geometric model for this B-way operator, Battalion-Minkowski. And this map, this property basically explains the algebraic structure for this quantum HKR, and for basically the quantum correlation map, or this topological correlation in this model. And for example, you can also show like if you specialize this H bar to a particular number, non-trivial value, then this is also quasi-isomorphic. And if you pass to homology, and this leads to a very famous formula by Feijin, Felder, Chocky, it's called a FSS trace formula. So that's the structure for this topological correlation. Okay, so that's the kind of thing we're gonna be working with. So next, I want to show you like this simple manipulation, this construction, how this is related to like index theorem. So we need to borrow a little bit geometry into this setup. So let me explain the first very naive, simple application to index theorem. So first, I can work with a more like general phase space by a 2n-dimensional symplectic manifold. So X is my phase space, omega is my symplectic form. So this is like curved space. But in general, this is this is a picture for the two sphere. So it is curved, but locally around any point, it's like the tangent plane is like linear symplectic space. So locally, it looks like linear, and it becomes the setup we have been discussing. Like, for example, if you work with linear structure here locally, then you can obtain some kind of wild algebra living on this tangent plane. So it's linear basically. So we can just do this canonical quantization. But for the whole manifold, you have different like patch of this manifold, and then have to somehow glue things together. So if you glue this local construction of this quantized algebra, like wire algebra, you can get a bundle of so-called wire bundle. So every fiber of this bundle is evenly ranked. every fiber of the bundle at a point is given by the wire algebra of the corresponding quantization on the tangent space. So as a vector space, so this bundle is given by this all these symmetric tensors of this cotangent bundle, and you have a fiber-wise Moyle product. So this becomes a bundle of associative algebra. It's the infinite rank. And so this actually, but this is too big. There's a famous construction by Farasov, which allows us to cut down degrees of freedom, and which leads to a version of deformation quantization on the phase space. This works as follows. So you see, like every locally you can have this algebra. Then Farasov shows the following: like basically you can construct a connection, like connecting two different local pieces, and make a flat bundle out of this data. So roughly speaking, he shows the following: like he can find some kind of one form value in this algebra, playing the role like a connection one form, such that so you start with any kind of a symplectic connection. So there's a connection which is compatible with the symplectic form. So this kind of thing always exists. Let's start from here, but this is no longer this is never flat. You can correct any symplectic connection to be a flat connection on a wire bundle by solving some curvature equation by finding this gamma. So this always exists. And this also called this one a Abelian connection. But once you have this one, then you can look at, for example, flat sections of this wire bundle. And you can show like the space of flat sections give rise to a deformation quantization on the symplectic space. So basically, you find associative algebra, which quantize the Poisson algebra on this phase space. So this is a simple construction on the symplectic phase space. But of course, like we know, deformation quantization exists on general Poisson manifold by the theorem of Kontsevich. But here we only work with a symplectic case. So there's some much simpler construction. Now, with this one, let's say we can basically glue all we have done like before to this geometric setting. So for example, every fiber we have a Y algebra, so we can look at this quantum HKR map. Basically, this map arising from this topological correlation, and then we obtain a fiber-wise like quantum HKR map. So this is a map of bundles basically. Then you can also linearly extend with coefficient like differential forms to a map from the Hausdorff chain complex of like differential forms valued in this algebra to differential forms valued in these fiber-wise differential forms. It's a little bit, the terminology is a little bit confusing, but it's basically extending the previous construction, like fiber-wise construction, by adding to these differential forms, basically. We want to work with like connections, flat connections, basically the modules. Then, but the problem is like this map is not compatible with the Farasov connection. So on the left-hand side, we have some kind of flat structure, and we want to construct something which is compatible with this kind of geometric, like flat structure. But it turns out like this naive one doesn't work. But it can be corrected by a standard construction, so-called twisting. So let me explain this twisting a little bit. So it's a very algebraic construction. Like suppose I have a differential graded algebra, like D is my differential. So given any element of this algebra, I can define the following operation on Hausdorff chains. It's by like inserting these A's at different places. So it's a dual to the inner product. So this is my operation lambda A. So basically, you insert this A everywhere in this chain complex. So with the help of this operation, you can define a twisting construction as follows. So suppose I have an element A, which is degree 1, and solve the flat equation, this Markov equation. Then I can use this particular A to do a twisting construction as follows. So I can basically they take a conjugate by this operation. So remember, my lambda A is the operation by inserting A everywhere at the one, insert one A. So if exponential of this operation basically is like a insert A like many times and everywhere, like all in all possible positions. And you can show this operation by twisting by A. And if you look at the conjugation of this operation with the for the original differential, like this is the differential from the algebra, and B is the Hochschild differential, you can find like after conjugation, it becomes again the Hochschild bicomplex where B is still the Hochschild differential, but now the differential of the algebra becomes the twisted differential. So the original D plus the commutator with with respect to this new A. So you see, like because A is basically a flat connection, so this twisted differential dA is still a differential, like still like square zero. So this construction is called a twisting construction. Like it's very standard process you can do for any kind of differential graded algebras or some kind of homotopy algebras. You can do similar constructions. So let's start from here. Let's see what we can do for our model. So remember, we have a so-called Fadasov connection, which is a flat connection on the wire bundle. Now, this is a new connection. It's a one-form valued object. So we can actually twist everything. So you see, like so far in the fiber-wise quantum HKR map, we haven't used the information from the connection. Now you see, like geometrically, a connection is sort of like a twisting. So we can use this Fadasov connection to twist all these homological constructions. And indeed, it's true. So we can twist the Hochschild chain complex of my Y algebra, like differential form valued Y algebra, using this Fadasov connection. So this is my operation, like twisting operation by this Fadasov connection. It acts on the Hochschild chains. And because of this H bar order, like I need to have to incorporate this negative orders in H bar. So this some natural operations you can write down. Then with the help of this twisting, I can twist my original fiberwise like topological correlation, fiberwise quantum HKR map. So remember, originally we have this kind of fiberwise wire algebra mapped to fiberwise differential forms. That's the HKR map. We can twist the fiberwise HKR map by adding the information from the twisting of the Fadasov connection. So this is basically coupling algebraic structure with geometric structure. So if you couple these two, you couple the algebraic structure with the geometric structure. If you look at the composition, so let's call this one Fadasov twisted quantum HKR map. And this map actually will have some magic property. So let me try to explain what this one is. And this is eventually related to index theorem. It's about this map. Okay, so if you study this map, you can show like so. You see, like this is my chain complex for differential form valued Y algebra. So this is like the first map is like a fiberwise HKR map, and then composed with the twisting. So this is my twisted HKR map. You get the fiberwise differential forms. Now, for this fiberwise differential form, I just mentioned like you can do this fiberwise B-way operator. That's the lead derivative with respect to the fiberwise Poisson bivector. And then if you there's a standard way in physics, which whenever you have this kind of B-way algebra, you can do a so-called B-way integration along some Lagrangian subspace. This Lagrangian subspace is related to gauge fixing condition. So here precisely is a Fermatic integration on forms, fiber-wise differential forms. So you can compare the differential forms here with the volume form from this symplectic structure. So that's a Fermatic integration or this Brazilian integral. So you can integrate out this fiber, you get a differential form on the base. So this process basically is about computing topological correlation, and from the first arrow, the second map can be viewed as the integration on zero modes. That's the Brazilian integral. Eventually, you obtain a map from the Hausdorff-Chern complex of this Y algebra to a differential form on the base manifold. So this composition is a red symbol here. You can show this composition basically intertrains. For example, here is the D is the flat philosophical connection, B is the Hausdorff differential. So this combination intertrains this Hausdorff complex of the Y algebra with the very simple differential, like just the RAM differential on differential forms. And everything is very natural, actually. So in the middle, there's something more complicated. It's basically, you can find that in the middle, it intertrains for example, this symplectic connection with the correction by this BV operator, and some additional correction by the curvature. It can show this also defines a flat structure. The whole thing square is zero. But this so far, this map is not important at this moment to understand what's happening. So we basically find for this composition a chain map intertraining the Hausdorff-Chern complex, this drum complex of the Y algebra, with the drum complex on the base manifold, and that's the stuff. So what's the metric here? So the metric is the following. So if you like this map is a chain map, so it can pass to homology. You can pass to homology on the left hand side and homology on the right hand side. And then we know the RAM homology of the like the differential, like the homology on for differential forms is given by the RAM homology. So we're gonna pass to the top the RAM homology, and then we can integrate on manifolds. Then if you pass to cohomology, you find the following. So left hand side, you restrict to the zeros cohomology. It's like flat sections. Then eventually you find a trace map, which maps a flat section of this Y algebra to the right hand side, because you map to differential forms by this process, and then so this composition gives rise to a differential form, and you integrate on X, get a number. So this map actually will play the role of basically the trace of this quantum correlation for quantized operators. So this is the trace map, which is basically a combination of this algebraic and geometric data. So you can show, for example, if you compute the star product, basically, by the way, I just mentioned these flat structures, the flat sections form a deformation quantization. Like, so the fiber-wise Moyle product preserve the flat sections. So we do have a associative product for the which is like a star product, and can show, suppose S1 S2 a compactly supported object here. Then if you compute the trace, S1 star S2 equals S2 star S1. So that's what the trace supposed to be, right? I mean, that's the kind of structure we expect. So you can show this one easily. Or you need a little bit uh, calculation on this Hausdorff homology, but that's a straightforward calculation. Then you can compute, for example, once you have a trace map, let's compute trace one. Trace one in physics is related to the partition function, and this trace one basically models this partition function for a topological quantum mechanical system on the symplectic manifold X. And you can calculate this partition function, trace one, using a BV analog of this localization argument. And eventually you find the following formula by computing this trace. This is like a Arif genus, and this topological class. And this omega h bar is a two form, starting from minus omega and plus some higher order corrections, which is a two form, it's closed two form. It parameterizes what kind of deformation quantization we work with for on this phase space. So you see, like this formula looks very familiar, right? I mean, actually, this is a special form of so-called algebraic index theorem established by Fadasov and Ness-Sigan. This is called algebraic index theorem. It's the algebraic analog of Atiyah-Singer index theorem. And of course, you can also like add into more data. For example, you can incorporate a bundle on X and to get chain characters and things like that. This also works, but this is only the simplest case. So actually, this algebraic index theorem is pretty strong. And later, like Ness and Sigan, they showed using microlocal analysis that this algebraic index theorem implies the analytic Atiyah-Singer index theorem. So this is actually quite interesting result. So you see, like this is how this topological correlations in the simplest model, this topological quantum mechanical model I explained, how this is related to index theorem. So this is the first instance of index theorem. But this index theorem sort of was known in the literature. But now we want to move on to something more exotic, like this is a quantum mechanical system, it's one-dimensional quantum field theory. We know like if you go beyond one dimension, like you go to two-dimensional higher dimensions, like in physics, we have many more examples of partition function, which is supposed to be some kind of index theorem. For example, as what Witten explained, if you calculate the torus partition function, supposed to be some kind of index theorem for Dirac operator on the loop space. So imagine like this is algebraic index theorem. Does it work to that direction? So if you go to higher dimensional case, for example, if you move from quantum mechanical system to conformal field theory, does this work? And do we have an analog of this algebraic index? And the answer is yes, we can find some algebraic analog. So let me just briefly discuss this work. And basically, I will say a few words about this chiral conformal field theory and what we call this elliptic chiral index. So here is a picture to compare these two situations. So in the one-dimensional case, like we have for example, we work with circle, and the quantum operators living on a circle, they form basically an associative algebra. For example, like you can have left and right product representing like how points collide as local operators. This is OPE basically. And in two-dimensional case, the situation is very different. You see, like in two dimensions, we don't have left and right, right? And you can work with like topological 2D topological field theory or some other like models, like for example, chiral theory. So in the case of chiral CFT, if you look at the OPE of 2 points, so when local operators they collide, if it's not topological, it's a chiral case, means like when they approach each other, there's some kind of it depends on the location holomorphically. So we can write down some kind of expansion on the right hand side, and basically represents like a Fourier mode. Like you can, for example, the point can collide to the other point by winding around like a couple of times. So the winding number, the Fourier mode, give rise to infinite tower of like binary operations. And this is a so-called operator product expansion in the in the case for example for what is operator algebras. So that's the kind of structure, the algebraic structure we expect in this 2D theory, like the 2D chiral theory, for example. Now I can again ask the following question, like, okay, let's try to figure out differential operators here in this 2D setting. So actually, the chiral analog of differential operator in 2D is the so-called beta gamma system. And then the chiral analog of Clifford algebra, for example, is so-called BC system. So one of them is bosonic, the other one is fermionic. So I'm gonna focus on this particular situation, like say the chiral analog of differential operators and Clifford algebra. So I'm gonna focus on beta gamma and BC system. So I'm gonna work with the particular Riemann surface. For the purpose of index, I'm gonna work with like a elliptic curve, a torus, basically. So you can find something quite interesting. So here's the theorem I want to explain. John worked with my former student, Zheng Ping Gui, in this work, like elliptic trace map on chiral algebras. So basically, we work with, say, beta gamma BC system on an elliptic curve. So tau is a point on the upper half plane, which is indicates the moduli for a complex moduli for this elliptic curve. So we consider beta gamma system or BC system. So we basically look at the chiral analog of differential operators or Clifford algebras. Now there's a analog of this Hochschild chain complex in two-dimensional case. So remember, like previously, we can plot like we can place these operators on the circle and and then look at the way they collide, and that's basically how you draw this Hochschild chain complex and Hochschild homology. In two-dimensional case, it's very similar. You can write down many points, put many points on the curve, and look at how they collide, and remember the way they collide by, for example, writing when points collide, you can calculate the OPE and compute the residue, for example, and then you can write down something very similar. So just look at how points collide. You can write down a chain complex, and there are many different versions of this chain complex. And there's a general version is given by Bennington-Drinfeld for this chiral chain complex, and I'm using this one. So this is so-called chiral chain complex. It's very similar to what I just described. The precise definition is very complicated, but the idea is very simple, just like that. So I basically place these operators, like representing like a higher analog of differential operators on the elliptic curve, and write down the following chain complex. Again, similar to this topological correlation on the circle, we can look at an analog of this correlation on the elliptic curve. And it's not quite topological, it's chiral version of this one. And then you can show this map. Map to by the way, I didn't explain this one. The right-hand side is a particular algebra. I don't, you can write it down explicitly. It's basically the so-called algebra on the zero modes. So it turns out to be a BV algebra. It's a finite dimensional BV algebra. And if you know something about quantum field theory, this map is a map where on the left-hand side is some kind of local structure, and it's kind of algebraic structure in the UV side, ultraviolet side. The right-hand side is basically algebra on the zero modes. So basically, it is an algebra on the infrared side. So this correlation map basically is the integrating out modes, pushing from UV point to IR. So it's this another way to say this integration map in the in terms of quantum field theory language. So you can show this map is very similar to what I just described for topological quantum mechanical model. This map, roughly speaking, is given by computing local correlations on the torus, And you see, like the thing which is different from the quantum mechanical case is we know like if you compute local correlations in this conformal field theory, it could be very singular. Like say, for example, when points Z1 approach Z2, it might exhibit, for example, like a pole of order like 1 over Z1 minus Z2 to the power of like 2025, for example, like that. It could be very large. It could be very singular. And then I use a special notion, which I call this regularized integral. So in particular, it's a basically a geometric way to renormalize this integration. So basically, I want all points run on the torus. So remember, like the way we discussed HKR for this topological quantum mechanical system, we put things on the circle and let them run. The things here is very similar. We put things on the torus and let them run over all points on the curve. But because it's singular, we have to somehow define this integration in a careful way. And this was done in my work with my colleague Jazo. We call this one regularized integral. It's basically a version of a Cauchy principal value, basically, in complex analysis. Then, with the help of this map, you can sort of see like this is basically leads to a Kaya version, a Kaya analog of HKR map. And it's also quasi-isomorphic. And if you, for example, if you compute the partition function with on particular glued on the target or sit on the particular background, you will see like Witten genus appears naturally, and that's what we call the elliptic Kaya index. So this is the Kaya analog of this algebra index for deformation quantized algebra in the quantum mechanical system. So here is a Kaya CFT, and you have this Kaya elliptic Kaya index on the EP curve. So yeah, this I think I won't have time to discuss this one in detail. If the precise construction is quite involved. So, but if you are interested in, so here's the reference. So, elliptic trace map on Kaya algebras. Okay. Yeah, I think that's all I want to share today. And thanks very much.
Thank you very much, C. So, any questions or comments?
Um, I have a question actually. In the beginning of the talk, there was a function f, f which was a function of momentum and position, right?
Yes,
Uh,
yes.
my question is, why didn't you choose in this probabilistic theory f to be only a function of momentum? But I mean, in this probabilistic theory of quantum field theory, why did we choose that f is only a function of momentum?
Oh, if you yeah, you can also play with just functions on momentum. But the reason I'm playing with like functions on the full phase space because functions on the phase space there are the low classical observables in quantum mechanical system, and they have for example this standard structure like Poisson bracket, and this is Poisson algebra. This is a classical observable. Uh, yeah, this is like functions on phase space, classical observables. So here I just want to show you like from classical observables, if you throw them into this machine, you find basically structure for the corresponding quantization, the quantum operators. That's all I want to explain. Yeah.
Okay, thank you very much. It is about quantization that we require. You require, here, XT.
Yes. After I
Hmm.
really, that's right. Because in the quantum case, like X and P, they don't commute, right? The commutator is H bar. So that's why you
Hmm.
have this all
Okay.
this kind of yes, where's the yeah, this so in the quantum case you find this quantum product basically. This
Okay. Thank you very much.
yes, thank you.
Any more questions or comments? So let's think, see once more.
Okay, thank you. Yeah.
Thank you very much. I mean, this is a very interesting talk. Actually, I heard about Moyal product many years ago from a professor in Ankara University. He
Huh?
was working on deformation quantization,
Yes,
and he was interested in Kontsevich work. And
yes.
it's a nice again seeing that. So. We will meet 2 weeks from now again, but this time 6 o'clock Istanbul time, this time, next meeting.
Yeah.
So, see you all later, and thank you. See you again. Yeah.
Okay, no problem. Yeah, good to see you. Thank you.